So now let's move on to metal alkynes. And maybe I'll go back to the notes in a minute. Let's talk about the alkynes first. Then we'll go look at the pictures that you guys have in your notes. Okay, so an alkyne, that's going to be a carbon with some form of triple bond. So you're using these electrons to make a bond. So you can either be a 2-electron donor, but remember you have a whole other one over here as well. You can have a total, it's either going to be a 2-electron or a 4-electron donor, depending on how much is being given to the metal center. So looking at your pictures, just bear with me. Let's share our screen. Okay. There we go. Okay, so can you see over in this case here? It'd be easier if I had a mouse. So our sigma donation. So here it's broken down. So one of those, it was a triple bond. Okay, so the third bond they're showing instead as this pi orbital. Okay, they're showing that really the 2p orbitals, but it's kind of like giving us a pi orbital. So that is donating into some metal orbital. In this case here, the t z squared. We have to have a similar symmetry and similar phases. So that's your sigma donation. You can also have sigma donation like this as well. So sorry, this is pi. So this first one is sigma bond. The second one, you can also have a pi bond. Okay, so it's not a back bonding. This is a pi bond from the alkene or alkyne to the metal. So we're always looking at the different phases and symmetry of our molecular orbitals or our different orbitals on the metal versus ligand. So in this case here, you can have a pi bond. So you're going to write sigma bond for this one. This one is a pi bond. Make sure you're writing that down. Now it can also act as a pi acceptor. So here's our pi star orbital. Remember the phases are reversed. You can have pi donation from the metal to the ligand in that case. Okay. So this is pi bond coming from metal to ligand, so back bonding. This one here, a little bit different. Okay, it's hard to see. I'm going to kind of use my hands. This is like having on an angle like this. Okay, so it's not like it's coming like this on it. It's like this. Remember our delta bonds that we talked about when we were talking metal-metal bonds? So this other one right here is now a metal or a delta bond. Okay, so you're going to have back bonding from metal to ligand again, but that's delta. You have sigma, pi, and delta. Okay, and again, just like those other cases, stop sharing the screen. You can have kind of one extreme to the other. So let's say you have your first one. Very simple 2-electron donor. And as you increase that back bonding, you're going to go to that other extreme where you're going to have, you've broken one of those pi bonds between the carbons. Remember, you also have one more thing that's sticking off in some way. So this would be metallo cyclopropene. Okay. Now, let's move on to the next set, which are the conjugated dienes. These are a little bit hard to see, but I do have some pictures here, and I do encourage you also to go to your textbook and read these sections because there are more pictures there and also more description of what's actually going on. I'm giving you the Coles notes version. So for our conjugated dienes, we're talking about the 1,3-butadiene. Okay. So that's this guy right here. We're talking 1, 2, 3, 4 if we're labeling our carbons. So the most common, I guess you could have, if you think about what's happening here, you have, we just looked at alkenes, right, binding. So you have really 2 double bonds that can be donated to a metal center. Think about it, right? So this could be more common, 8 of 4. So all 4 contributing to bonding situation. And the number of electrons that would be, it's 2 per pi bond. So you're talking about a 4 electron donor max. Now let's go look at the picture. I'm going to kind of try to explain it. Well, first of all, I'm going to draw out, you have 4 molecular orbitals. I'm just going to fill those in. So this one is your HOMO. There is your LUMO. So let's go to these guys on the page. Okay. Sorry, a little bit slow. So there's our picture in this case. Now, you see that one right there. Good. Now, on the bottom, it's hard to see. There's a pair of electrons down there and a pair of electrons in the HOMO as well. This is just showing you the molecular orbitals involved just in butadiene by itself, not bound to a metal. So you have this really big delocalized pi bond that goes the entire length of the molecule. So you can see how you can get nice sigma donation from one of these to a metal, okay? Probably the dz squared. So I'm actually going to write that down up on here. You guys might not be able to see that now, but I'll make this go big later and you can then write it down. So that bottom one is going to be sigma donation, okay, to the metal, probably dz squared. Okay, that's what's going on in that bottom one. Now, the next one up, looking at your different phases and the symmetries that you're going to have, this will now be a pi bond. It's going to be pi donation from the ligand, because the ligand's going with the electrons. So from the ligand to the metal, and you're going to have to use one of those planar, so the metal XZ orbitals. Okay, so this one here, and I'm going to write it down now. This one's going to be pi donation to metal D, X, and Z. Now, if you go up and look at this one here, so this is our first set of antibonding orbitals, but you can see you also have increased electron density between C2 and C3, right? So what's different here? Now, this is going to be back donation because this is empty here. So it's going to be the metal donating back into here. So this will be pi back donation, probably from the metal DYZ. So put that here, pi back donation from metal DYZ. And our top one is the complete antibonding picture. And in that case there, so you see you have positive, negative, positive, negative. Remember, this is planar. So if you now picture your dxy, so right underneath it, kind of like sandwiching it, if you remember what type of bond that is, it's not pi, that's a delta bond. Okay? That's going to be delta back donation. I can write that one down too. Delta back donation from metal dxy. Okay, let's go back, stop sharing the screen here so you can see what I've done on the board. So here's the different situations that are occurring. Write some stuff down over on the side. If you think about, actually I probably should have kept that picture up there a little bit longer, but as you are donating here, you're lengthening, so C1, C2, and C3, C4 end up being lengthened throughout this process. And remember this LUMO one, if you look back in your notes, you saw increased electron density between C2 and C3. Well, what ends up happening with increased back donation is you end up shortening C2, C3. okay? Lengthening the other guys. So that's what's happening there. Now, I'll show you those kind of, if we do the oxidative addition on something like this, we go from that purely just sigma donation, pi donation, to adding in a full pi back donation. Show you what that looks like. So it's kind of hard to picture here. I'm going to draw it, try to draw it a little bit flat. Okay, so picture your metal underneath, just like that. Okay, so your metal is being bound to that one and through that one. It's kind of like a bit of a sandwich. Now, as you increase your back bonding, what ends up happening, where you're starting to make bonds between these guys on the outside, lengthening these, shortening that one back there. So ultimately, you end up with this situation right here. So you still have that kind of 8-2. That's terrible in the background. Okay. But you've now increased your oxidation state here at your metal. You've done an oxidative addition. So this is now a metallocyclopentene that we just created.